expressions in the meteor. Every page.
Okay, so for the meteor problem, I'm going to post the full solution to that. So if you have questions, that should answer a lot of them. If you still have questions, then don't hesitate to ask us about that. But I'm not going to take class time to go over the meteor sheet because of the solution will be posted soon. And then the other part is transitioning into what we're about to work on. So let's just start though by reminding ourselves what the meanings of these expressions are. So let's just, as an example, this one right here. So I want you to get a partner and tell your partner, explain and take turns. What is the meaning of that expression that I put in the blue box? Okay, what is the meaning of that expression that I put in the blue box? Go, get a partner, practice explaining that. Go. Okay, so first question is, what is that? So is that a function? Is it an equation? Is it a value? What is it? What is it, first and foremost? Is it a function? She says it's a number. Is it a number? People are nodding. Yes, it's a number, okay? So let's say, is the value of what? So that thing in that is the value of what? Who thinks they can explain that well? Yes, sir.
All right, so if you took the antiderivative of this function, it would give you a graph, and this would be the change in y on that graph.
Okay, so it's the value of?
Like the original function's change in y.
Okay. The total change of some quantity. Is that all? Is there more? So he's saying that's the total change of a quantity. Let's finish it. So it tells us more than that. Yeah, Adrian.
Between 0 and 8
when x changes from 0 to 8, and the rate of change is 3 e to the x. Team effort. So this is the value of the total change of some quantity when x changes from 0 to 8, and the rate of change is 3 e to the x, or with a rate of change of 3 e to the x. Okay, and we can use the fundamental theorem to figure out what that value is, right? So this expression just kind of represents that how does that expression represent that value? So like what process is that expression showing that to represent that value? Yeah.
Adding up a series of very tiny changes.
Right, adding up a bunch of small changes. And where in that expression do we see one small change? Where in that expression do we see? dx, that's one small change that we're adding up. We're adding up changes in x? No.
That the expression gives you.
What's that?
The value that the whole expression will give you is the little changes in y that you're adding.
Okay, so can I see a little change in y somewhere in that expression? Where do I see that little change in y?
The whole 3 dx.
Yeah, right? dy equals m dx. Right? That's how we're calculating those little changes. And where's that? M dx. So that's one little change. That's one little change, dy. So we're adding up. The integral sign means sum, German S, for summing up a bunch of little changes in our quantity, a bit by bit by bit, by using the rate to do it, right? A little constant rate times a little change in x. The next constant rate times a change in x. The next constant rate times a change in x. That was all that process that we worked through with the pretend rate function, the constant rates, and adding up the changes, right? So that's where that all comes together in this expression. Any questions? All really important. Because we're going to be doing lots of integrals this semester, so we should know exactly what we're looking at when we look at an integral. Okay. So you did some practice on derivatives and then got your feet wet with some antiderivatives. So let's just do this again. So I want you to use the chain rule to find all the derivatives of these three functions. Okay, use the chain rule. Don't use the quotient rule for number one. Only use the chain rule, not the quotient rule. So you might have to rewrite that first one. Start by rewriting it as something to the something, right? And then you can use chain rule, okay? So take a couple minutes. We want to review the chain rule because all these, so we want to base all our antiderivative skills on a really good foundation of derivative. Like, so we want to be thinking about working backwards. So we want to really get derivatives down. So what are the derivatives of each of these? You can work together, by yourself, whatever you want. Okay, yeah, sure. The exponent is 3x to the 5/4. That's 3x to the 5/4. Okay, so compare with the person next to you. Okay. So I got my list here. Where's Alec Hutchings? Where's Alec? Alec. Okay, we're gonna regroup here. How did you rewrite that first one before you took the derivative? Did you do that?
I turned it into all of what's in the square root
Yep.
of the negative 1/2.
He wants an exponent of negative the 1/2. Agree? And then what, Alec, would you get for the derivative then?
Negative parentheses x to the 5th minus ln of x plus.
Wait, start again. Negative what?
Negative parentheses x to the 5th minus ln of x plus pi to the negative 2nd. And parenthesis, starting parenthesis 5x to the 4th minus 1 over x minus 2 pi to the negative 3rd and parenthesis everything over 2.
Okay, so first of all, what about what's going on here? So
That was
are you using the power rule here?
yeah. I did the derivative second and left the
Oh, when you said the whole thing over 2,
yeah.
this is the
That was the 1/2.
okay. And then what about, is there a power on this thing?
No, I left that as a regular function and then took the derivative.
So when we do the power rule, we're going to do negative 1/2 times that,
Oh, sorry, it's the negative 3/2.
negative 3/2. And then what's the derivative of pi to the negative 2?
0.
That's just a constant, right?
Right.
So what do? We did the derivative of the big picture, which is something to the negative 1/2, leaving the inside as it is, and then we multiply by the derivative of the interior. Agree with it? Next one. Where is Adrian? I don't know. You're over there.
I haven't done this one yet.
Okay. Very good. How about Trevor? Trevor Hoke. Where are you?
So, I don't really know how to explain it with the rules, but you're going to have like e to the 3x power of 5 over 4.
Right.
Then you're going to multiply that, and then you're going to keep the 3 constant,
Okay.
but it's going to be times by 5 over 4.
Good.
X to the 1/4.
I do 15/4 then? X to the?
1/4.
How do you do? Again, what do we start with? We start with the derivative of the kind of the exterior function, or in the big picture, which is just e something, right? And the derivative of exponential function is just itself. Derivative of e to the x, e to the x. So that's how we're going to start. E to the 3x to the 5/4, and then times the derivative of the interior function. Okay, good. Where is Miranda Little? How'd this last one go?
I got secant squared of cosine x times negative sine x.
How'd you do? Same. See, this chain rule is this pattern of if you take the exterior function, the derivative of the exterior function, derivative of tangent is secant squared, leaving the interior as it is, and then what? Something pops out, right? Chain. This is where the chain comes on. We're chain on the derivative of the interior function, negative sine x. Everyone good on chain rule? Because what we're going to work on is probably the most important technique in terms of antiderivatives, which is undoing these. So we're going to think about, we're given something like this, we have to recover the original function. And you did some of it a little bit, you got kind of started doing that in your homework, right? So I want to give you, we'll keep doing that, but I'll give you a little bit of structure because some of these get a little complicated. Okay, but this is the idea that we're gonna start with a function like this, and to get its antiderivative, we're gonna have to collapse it back together. And so let's investigate what that will look like. Any questions on these derivatives? Okay, here we go.
You start your recording.
I think so. Thanks for asking. Yes, I did. Okay, so what does the chain rule say? G of f of x, the derivative is, how about Ryan Dykes? Where's Ryan?
The chain rule would be g prime f of x times f prime of x.
Okay, you nailed it, right? So exterior derivative, leave the interior as it is, times the interior derivative. So if we're going to undo this, this is what it's going to look like. We're going to start with something that's like g prime f of x, f prime of x, and we want to recover g of f of x. Make sense? So what are you going to focus on? So we're going to be given this thing, g prime f of x, f prime of x. What are we going to focus on in order to recover this amount or quantity function? Right? This is like rate of change back to amount. So are we going to focus on, we need to get g of f of x. So we're going to focus on, are we going to focus on exhibit A here or exhibit B? We're going to, right, because look, exhibit A is almost the answer. What's different about it? It's just that the exterior function it's the derivative, and we need g. What about the interior? Stays the same, okay? And so when we go backwards, this thing that popped out is just going to collapse back in, right? So it's going to be gone. So when we went forward with the derivative, f prime popped out for this extra factor. But when we go backward, then that's just going to pop back in. So we're going to focus on this part of it. We have to identify and focus on this part of it in order to recover g of f of x. So what will the approach be? So we're going to write what? We're going to write the antiderivative of the exterior function, right? So we're going to be given some of this function, g prime f of x. All we really need is the antiderivative of the exterior function, and we got to leave the interior function as it is. And we'll have it. Well, almost, right? There may be a little mess to clean up, and we might be off by a factor or something that we have to figure out. But this is 80% of the thing. Okay, so then we're gonna take. You'll see how we do this. But this is the general idea. So this says the same thing as that was on the last slide. So let's try an example. So here's x cubed times 8 plus x to the 4th to the 5th. And we're considering this rate function here, right? This is the rate of change function. We're considering it to be like this whole expression here. So which is going to be our g prime f of x? Is it going to be exhibit A, x cubed, or exhibit B, 8 plus x to the 4th to the 5th? Which looks like this. So a composite function whose interior derivative is the other factor, right? So which is a composite function whose interior has its derivative somewhere else. So you should be seeing that that's this. Many of you said B, and you're right. So this is like our g prime f. And we can just briefly check that before we get started. What needs to be true? Then this essentially needs to be the derivative of what's inside. It could be off by a factor. But is x cubed essentially the derivative of 8 plus x to the fourth?
Yes.
Yeah, right? Because the derivative of 8 plus x to the fourth is 4x cubed. So we're just off by a factor there. So what are we going to do? We've isolated our g prime f, so we can make a first attempt. And what will our first attempt at the antiderivative look like? We're just going to do what the antiderivative of the exterior function and leave the interior as it is. So what will that first attempt look like? Where is Ralph Kissel? You know what that first attempt would look like?
I'm not positive. I want to say like 5 times in parentheses 8 plus x to the fourth.
Okay. To the what?
To the fourth power.
All right. So now so you got the right idea, but you took the derivative, right? Now we're doing antiderivative.
Oh, okay.
So what would the antiderivative be?
So this is the 6th.
Sixth, and then we'd need
1/5 or 1/6.
1/6. So that's our first attempt. We do the antiderivative of 8 plus x to the fourth to the fifth, which is 1/6. 8 plus x to the fourth to the sixth. And so now we're going to check it. How can we check it? Take the derivative. So if the derivative that we get is exactly what we started with, we're done. Our first attempt was right. So what's the derivative? 6 times 1/6. Here's our chain rule again. 8 plus x to the fourth to the fifth times what? 4x cubed, which equals 4. Is that identical to the rate function we started with? So now the question is, what do we need to do to our attempt? How do we need to adjust our attempt so that if we took the derivative, we'd get exactly what we started with? So what do we need to do to adjust this temp so that when we take the derivative, we get this? We have an extra factor of 4, right, that we don't want. So that means we need a factor of 1/4. And if we checked it, we won't go through it all, but it would be right, okay? And so then we can simplify this to 1/24, 8 plus x to the fourth to the sixth. And if it's not a definite integral here, so we don't have values here, what that signifies is what? All antiderivatives of this rate function. All antiderivatives of the rate function. So to get all antiderivatives, we need plus c, any constant added to it. Okay, so there's this structure that I'm giving you, and so many of you are going to need this structure to get started. You make your first attempt, you check the derivative, you make a second attempt based on the check. But really the goal is that you could look at this and see this as the result of a chain rule derivative, and you look at this and go, oh, okay, I know what this is going to be. It's going to be what I'm going to need. This is going to be the 6th power. I need a 1/6, but I'm also going to need a 1/4. So kind of the goal is that you're just doing the chain rule backwards, and that you could just eventually just write that down. But if you need the structure in the meantime to practice, that's fine. But we're really thinking about undoing the chain rule. We've got this what function, when we did the chain rule, would give us that. Okay? Anybody have a question? Try another example. Here we go. So why is this one a little different? What's going on here? Well, it's a fraction, right? Chain rule, we're used to it being a product when we're all done. So can we get that into the form of a product? Multiplication. Let's see. How about Kelly? Kelly vote. Where's Kelly? Can I rewrite that as a product? Cosine x divided by sine x to the fourth. Not sure? Okay, where's, how about Philip? Can I rewrite that as a product, Philip?
Cosine x times 1 over sine to the fourth x.
Okay. And can I do it without the 1 over even? It's to the fourth in the denominator.
Oh, yeah, make it negative.
Sine x to that.
Negative 4. Sorry.
No problem. Okay, and so now it's looking like the result of chain rule instead of that fraction, but those are equivalent. So are we going to focus on cosine x, or are we going to focus on sine x to the minus 4? And what is the antiderivative of sine x to the minus 4? Just the exterior part. How about, where is the other Alec? Alec Warren.
So you're going to want to first write it in parentheses sine x to the fourth, or sine x, close parentheses, and then add 1, so it's going to be negative 3.
Good.
And then on the other side, put negative 1/3, cancel out, that will eventually cancel out. There's your antiderivative of sine x to the negative 4th.
So is there more to it? Is this it, or is there more to it? That's it. Okay. So then, check. Let's check it. Derivative. Negative 3 times negative 1/3.
So that sine x and then cosine
Times.
times cosine x.
And then that equals, is it exactly equal to what we started with?
Yes, sir.
Okay. But we want all antiderivatives, so plus c. So that, and that one, first attempt got it. Wait, that's not the answer though. So what's the answer? Sorry, that's not right. That's the check. That's the original rate function. So then our answer is
Negative 1/3 sine x and negative 3 plus c.
right. And so here's the beauty of this. You don't have to be stressed about making sure it's right, because what can you do? You can just take a stab at it and then what? Take the derivative. And that's what this is based on, right? So we just want to get at something close. Yeah, and you don't have to be all apprehensive. Oh, I'm not sure if this is right. Well, give it your best guess, and then take the derivative and compare it to the original rate function, and then make an adjustment if you need to. Any questions on this? Next one. Okay. You try it. Where's Natalie? Natalie Akram? Did you make a little bit of progress to get me started here? Did you rewrite the integral? First of all, as a product? No? Okay. How about Farah?
Yeah.
Did you get started? Tell me.
So I rewrote the problem into integral of 6 times 2 minus 9x to the power of 1.
Power of
Negative 1.
-1.
And then if you were to take the antiderivative of that one section to the right side, it would be 2 minus 9x to the power of -2 divided by -2.
Okay, so we're talking about now antiderivative of something to the -1. So if you went to -2, that'd be like derivative, right? Because you'd be reducing by 1.
Yeah, sorry.
So what is our antiderivative of something to the -1st power? Yeah.
It would be natural.
Yeah, so you gotta, so if we were to raise power, so let's just try raising power. What would we get? 2 minus 9x to the 0. And then over here we'd need 1 over 0. It's getting worse, right? So, but this is great because this is like all your red flags are going up, that something's not right, something's wrong. 2 minus 9x to the 0 is simply what? Anything to the 0 is 1. So there goes our expression. 2 minus 9x is gone. That doesn't feel right. And then to add insult to injury, we're going to multiply by 1 over 0, which doesn't make sense. So it's like red flags. Something's different here. Something's wrong. So this is the one case where you don't use the power rule, and you remember what kind of thing gives you a derivative of to the -1st power, or 1 over, right? 1 over. And he said up here, what is it?
Natural log.
This is natural log, right? Natural log has a derivative of 1 over that thing, or that thing to the -1. So our first attempt, why don't you take over? What's our first attempt then?
6 natural log, the absolute value of 2 minus 9x plus c.
So we'll do the c at the end. How about?
Yeah, that's what I said.
So and when you do natural log, you had to, there's a domain issue there. Natural log is only defined for argument values greater than 0. But in this original expression, we don't have that restriction. So our antiderivative shouldn't have that restriction either. So this will take care of that. So we need the absolute value. And so then when we do and then we'll just keep the 6 along for the ride here. And then we'll do our check, which is 6 times what? 1 over 2 minus 9x times chain rule, right? Times -9. So that's the derivative of that thing. 6 times 1 over 2 minus 9x times -9. Is it just like this? And if not, how do we adjust? So how am I going to adjust it? Where's Tyler Bennett? Tyler, how will I adjust this initial attempt so that this -9 won't be here if I took the derivative?
Divide by -9.
Good. So it'll be, so what's our second attempt?
It would be 6 and 2 minus 9x
Uh-huh.
over -9.
Good. So can I do 6 -9ths like that? So second attempt here. Second attempt is this, which is -2/3 natural log 2 minus 9x plus c. And I'm not checking it because I know it's right, but don't hesitate to check even the second time. Okay. Do the derivative again and make sure that you get what? Exactly the rate function you started with. Questions on that one? A little more challenging. See what you can come up with. So this one's a little bit harder to see. So why don't you get a partner and hammer it out together if you're ready to do that. Or if you need to keep thinking by yourself, that's fine. But see if you can figure it out together.
I don't know what would give you potential.
Okay, so what's a little more tricky about this is neither of those look like a composite function. Neither of those look like one thing plugged into another, right? It's just tangent inverse, and then 1 over 1 plus x squared. So a question here that might help us make some progress here is, what is looking back at this thing, what would have to be f, and what would have to be f prime? So looking at tangent inverse x and 1 over 1 plus x squared, can we figure out, maybe let's start with f prime. Which one would be f prime? Where do we see one thing as a derivative of another, right? Because in the chain rule, the derivative of the interior pops out. So where are we seeing f prime there? You should see that 1 over 1 plus x squared is like f prime, where f is tangent inverse x. Do you see that? So then what is our focal factor there? What are we going to, this is, right, this is like f of x, and this is like f prime of x. But we know what we really are looking for is what? G prime of f of x. So what is G prime? He has an idea. Anybody else? I bet he's got it. Anybody else think they got it? These two guys here? What do you think?
I want to say it's arctan, but I could be wrong.
Well, that's what this is. This is arctangent. This is arctangent.
Isn't it like the 1 over plus arctan of x squared?
I think it's like
Yeah. So this is arctangent x. This is the same thing as arctangent x. I'm sorry. So this is not. This is the one way of expressing arctangent x. So that's what f is. It's arctangent, or tangent, or the inverse tangent. So what is G prime then? Yeah.
Is it like the whole thing?
The whole thing to the negative one? But it's not in the denominator. But you're onto something there. It's kind of like the whole thing is to the
Power.
that would make it 1. But sure, this is the right idea.
Everything's to the first power.
To the first. And so then what's the first attempt? So this is like tangent inverse to the first, although that's not there. It's just like anything to the first power is itself, right? So what's our first attempt? So now we got our focal place to focus on. And what are we going to do? We're going to do the antiderivative of exterior function. What is it? 1/2 arctangent to the second power. If we check it, what do we get? 2 times 1/2 times arctangent to the first power times
1 over 1 plus x squared. Oh.
and that equals exactly the rate function we were given.
Over 1 plus x.
So that's it right there. You see what happened? No. Question? Is there a question?
I was, you know what I was thinking of when I said arctan? Was that like a something asking for the derivative of it? Because the 1 plus x squared on the bottom was familiar.
Right. It's the derivative of arctangent, which we have over here. So that's why this is f, and this is f prime. F is arctangent. F prime is 1 over 1 plus x squared.
Okay.
So what we're looking at is what arctangent and the derivative of arctangent, but we just had to figure out what this exterior function on arctangent was, and it's just to the first. If there's nothing there, then that's the same as it being to the first. So then the antiderivative is 1/2 that thing to the second. And then when you do the derivative, you get exactly what we started with. So let's trickier one. Okay, let's see if there's another one here. All right, so here's a only 50 minutes, guys. Could be an hour and 15. Okay, so culture bacteria in a particular dish has an initial population of 255 cells and grows at a rate of 50 e to the 0.3 cells per day. So our goal is to find the population 10 days after the initial measurement. So we have a rate function, and we need to get something to do with the population. So what can we do to make progress towards getting this quantity of population, giving this rate function? Okay, so before we talk about antiderivative, how can we express something that has to do with population if we have the rate function? Hector, do you know? Okay, so if we have the rate function and we set up an integral of that rate function, say, times dt, right? That's a little change in population there, right there. So then over what time period do we want to sum up these little changes in population? Okay, from 0 to 10. And will that give us the population 10 days after the initial measurement? Yeah. Yeah, what does this give us? So how would we interpret this? The change, right? The total change in population from 0 to 10. That's what that would mean. So if we want the population, then we're going to add 250. Right? So that integral gives us the total change in population from 0 to 10 by adding up all the little changes. And then we're going to add it to the initial population to get the actual population at 10 days. So now, how are we going to get that value? So find the value. Go. No calculator. I don't know why you're reaching for calculators. Right, use an expression, right? So just to write your answer, if you need to write an expression for your answer, write an expression. But we've got, so we want to apply what we learned in class today. We want to apply what we learned in class today. Where's Trista? Trista, did you get started on this?
Yeah, I was starting to take the anti-derivative
Okay.
of it.
And what were your thoughts about that?
So I know you would keep the e to the 0.3 to the t.
Okay.
And then think in the
And should we hold on to the 50 too? Okay, so okay, good. So you're trying to think it all the way through. So, but we know that what the exterior function is e to the something. So the antiderivative is just e to the something, right? It's just e to that same something. So we can make that our first attempt, and we could take the derivative, and then see you're kind of grappling with what do I need, right? So this would be one way to figure that out. But eventually, yeah, if you want to go for it all at once, that's totally great. But what is the derivative of this? 50 times 0.3 times. Okay, so is that the rate function we started with? So, Trista, how are we going to adjust it? So second attempt. We don't want that 0.3 to be there, so she's right. 50 over 0.3 e to the 0.3t. But now this time it's a definite integral, so we want the total change if this is our quantity function. So to get the total change from 0 to 10 for that quantity function, what do we do? Final value of the quantity minus the initial value. So it'd be 250 plus our 50 over 0.3 e to the 0.3 times 10 minus our antiderivative or rate, quantity function evaluated at 0. And that will be cells. Okay, anybody have a question on what I did? Yes, please.
It's just a simple one. Can we assume that we don't need to simplify unless specifically asked to?
Well, we probably should. Like, so you would never tell your friend, your scientist friend, oh, there are 250 plus 50 divided by 0.3 e to the point blah 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 cells in this dish, right? So yeah, so just for time's sake, I just stopped there.
Okay.
But it would be more appropriate to actually get a number of cells approximation and report that as the answer. Yeah.
This is like really nitpicky, but like, so if we're doing a word problem where you have to deal with something like cells and get it in decimal, you always round down.
Yeah, good. So now he's saying, okay, what if I got 350.3 cells? And you got to think about what makes sense. Is it really 350 cells or 351? So assuming that the cells are growing, then yeah, by the 10th day you haven't gotten that next cell yet, so you would truncate, right? You'd knock it off. But so you got to just think about what makes sense in the situation. I'm going to round up or round down. No, that's a good point. That's not nitpicky. Other questions on this? Okay, Blackboard has your next assignment. The first online homework is going to be due Monday, but I will post that before Friday if you want to get started on it, okay? But for Friday, you're going to have another worksheet from Blackboard, but then also problems from the book. So just read Blackboard carefully.